learning, we're also going to make the assumption that we're working with independent events for the time being. And then when we take a sample, we're taking a random sample. Not always the easiest thing in the world to take a true random sample, of course, because it's work to get a random sample. There's all sorts of ways to introduce biases and stuff so you don't get a random sample. So I'm going to ask you a couple of basic, you guys have been to Atlantic City. I'm going to ask you a couple of basic questions about, say, a coin toss. Okay, chances of getting a single head. If I toss a coin, what's the chances of getting heads on that toss? 50%. Okay, now let's say I toss a coin twice. What's the probability of getting both heads? They're independent events. The probability of the first event is 50%. Probability of the second event is 50%. So the probability of both of them coming up heads is 50% times 50%, 0.5 times 0.5, or 0.25, 1 in 4. What's the probability of all three coming up, tossing coin 3 times, and all of them coming up heads? 1/8, 0.5 times 0.5 times 0.5, 1/2 times 1/2 times 1/2. Okay, what about 10 times? 0.5 times 0.5 times 0.5 times, in other words, it's 0.5 to the 10th power, or 1/2 multiplied by itself 10 times. Everybody okay with that? Get the idea? What's the probability of getting 3 tails in a row? 1/8, same as getting 3 heads, because you'd have to have all 3 of those would have to be satisfied. All 3 of those independent events would have to satisfy that condition. Okay, so now, what's the probability, if I toss 3 coins, what's the probability of getting 2 heads out of those 3 tosses? Uh-oh, things got a little complicated, right? In other words, there's many ways of getting, I shouldn't say many ways. There's several ways of getting 2 heads from 3 tosses. You could get heads, heads, tails. You could get heads, tails, heads, heads. You could get heads, tails, heads, right? So we got more than one way of that happening. But all of those all the different possibilities, they're all independent of one another. So I can actually make a kind of a probability tree, which I'm going to do right now. And if you want to mimic this as we're going along, I'm going to look at all the possible ways that I might have an outcome for flipping a coin. Okay, so I'm going to draw this on here. Okay, and I hope you guys online are still hearing me and that you're going to do the same thing that I'm doing. By the way, you can type into the chat box every once in a while when I remember to. I'll glance over there to see if there's any questions and so on and so forth. I'm going to skip past this stuff a little bit. So I get a nice blank page. Okay, so I'm going to take a look at this. Okay, let's see. Okay, and I presume you can see that chart behind me. Good. I'm going to get this out of the way. Don't use this. Okay. Okay, so let's take a look at this. So now, when I toss the first coin, right, I can get either a heads or a tails. Heads or tails. Yes. Something happened? Oh, my goodness. Yeah, I don't know what this is all about. There's something installed here. I don't think they can see this stuff where they are at home, just us. Okay, so the first coin that we toss could be either a heads or a tails. Okay, now once we've tossed the heads, the next coin that we toss could be a head or a tail. Right? Same thing if it had been a tail, it could have been the next coin could be a head or a tail. Okay, well now if we toss heads and heads, so the next coin could be a head or a tail. And the next coin, if we toss a tail there, could have been a head or a tail. And similarly, a head or a tail. And a head or a tail. Okay, now what are the probabilities here? Well, the probability of tossing a head or a tail is 0.5. And the probability on the next coin of tossing a head or a tail is 0.5. And so this is 0.5 here. So 0.5 times 0.5, and probability of tossing another head is 0.5. And probability of tossing a tail is 0.5. And 0.5. All these possibilities of tossing a head or tail individually are all 1/2. 0.5, 0.5, 0.5, 0.5, and so on and so forth. So what's the probability again of tossing 3 heads in a row? 0.5 times 0.5 times 0.5, right? That's equal to 1/8 or 0.125. Trust me, if you multiply it out, that's what you're going to get, right? Everybody agrees with that. Okay, what's the probability of tossing 3 tails? It's going to be 0.125, right? 0.5 times 0.5 times 0.5. Probability of tossing tails on each event. Okay, so now what about all these others that are not 3 heads or 3 tails? Well, each one of them, let's take a look. We have each one of them, whatever outcome we have here at the end is always going to be 0.5 because all the probabilities are 0.5. So heads, tails, that's equal to 0.125. There's 1 in 8 chance of that occurring. Okay, let's say heads, tails, heads is going to be 0.125. And if I continue along here with all of these, they're all going to be 0.125. Each one of these outcomes is equally likely. Okay, the only thing is that even though each one of these outcomes is equally likely, let's see what happens here. This first possibility is 3 heads. How many heads in the second possibility? It's heads, tails, tails. That's 2 heads. How many heads in the third? Let's see. Well, that's going to be, if we get a tail, it's going to be heads, but it's going to be tails and then heads. So there's 2 heads there too. Well, how about heads, tails, tails? There's only 1 head there. When you draw this at home a little bit more carefully, it'd be easier for you to see. Okay, well, let's go down here. Tails, tails, tails. That's going to be 0 heads. Well, tails, tails, heads, going to be 1 head. Let's see, tails, heads, tails is going to be 1 head. And tails, heads is going to be 2 heads again. Okay, so now let's see. What's the probability? If I add all these probabilities up, what do they add up to? 1, right? 100. That's all the possible outcomes that we might have from this action of tossing this coin. Okay, so what's the probability that we're going to get 3 heads? 0.125, just as we estimated before. What's the probability of getting 3 tails? Well, getting 3 tails is the same thing as getting no heads, right? So these 2 are accounted for. What's the probability of getting 2 heads on 3 tosses? Well, it occurs here, it occurs here, and it occurs here. So 1/8, 1/8, and 1/8. The probability of getting 2 heads is 3 out of 8. What's the probability of getting 1 head? Well, it's going to be here, here, and here. That's also going to be 3/8. So again, 1/8, 1/8, and these 2 3/8 they add up to 1 also. Okay, so we can track these probabilities if we look at every possible permutation. Now, imagine if I had asked you to tell me what's the probability of getting 17 heads out of 25 tosses. Well, we'd be here all day, right? We need we'd have to spread paper out into the hallway. We'd get it confused 9 times. Wouldn't work very well. Okay, how many of you guys ever heard of binomial probabilities? Has that come up before? A couple of people cheated here, and they've had a little bit of exposure to the statistics before, obviously. The rest of you guys didn't hold your hands up because you haven't had that exposure to it yet. We're going to be talking about that later on in the semester. This is a binomial probability. Binomial means there's 2 possible outcomes. Could be heads, could be tails. We're going to apply that to a lot of situations as we move forward because a lot of what we look at from a public health perspective is a binomial outcome. For instance, male or female, right? Basic one. Diabetes or not diabetes. Cancer, no cancer. Asbestosis, no asbestosis, and so on and so forth. So a lot of stuff we're going to work with in the future is going to involve these kinds of binomial probabilities. Okay, but again, keep in mind a lot of this stuff we're looking at independent events, and we're looking at random samples. Okay, so we kind of went through most of this, I think. Okay, now let me ask you another version of this question. Say that the probability of persons insured is 80%, right? I'm going to say, okay, I'm going to pick a person out of the population. Probability that person is insured is 80%. In other words, the prevalence of insurance in that population is 80%. That's probably pretty much the United States, right? It's around 75, 80% nowadays. Maybe a little bit better, like since Obamacare slightly. So at any rate, so say that the prevalence is 80%. I pick a random person out from the population. The probability they're insured is 80%. If I pick another random person from a truly random sample from this population, pick another person out, what's the probability that they're insured? Also 80% because it's an independent event. Anybody, can anybody suggest an instance where that would not be an independent event? If they were related, right? If I took, oh, you two people over here, and they happen to be married because they're walking, they were at first, I've been married a long time. We don't walk together that much anymore, but, but maybe, but at any rate, so chances are, if you pick two people out and happen to be closely related or married, it's likely that they're going to have both be insured, more likely than if you had gotten a truly random sample. So we want truly random samples again. And let's assume that this is an independent event. You're going to take a true random sample. You're going to avoid just picking out people from the same population or group. And what's the probability that if you sample two people randomly, that they would both be insured? Well, it's 0.5 times 0.5 for the coin, right? So what's it going to be for insurance? 0.8 times 0.8. What's the probability three people would be insured? If you pick three people out randomly, all three would be insured. 0.8 times 0.8 times 0.8. What's the probability that you pick three people out and none of them have insurance? Bingo. Okay, right? We get that 0.2 times 0.2 because the complement, remember a probability of A, insurance is 0.8. Probability of A complement, the opposite of A, not insured, is going to be 1 minus that. It's going to be 0.2. Okay, assuming that those are the only two possibilities. It's binary. Yes?
So what would the answer if you three people about
0.2 times 0.2 times 0.2. Okay? Everybody at least fairly comfortable with that? Okay, good. All right. Okay, let's move on to the next document. Okay, and let me open that up. Okay, and we got another version of this. I'm not going to go into that. Let's get that out of the way. Maybe I will go into that. Yeah, not much time. I'm a little short on time. If you look at this version of this, let's take a look at how this differs from. This is the probability that a person would take a test. And let's see, and that there's a 20% chance they would get it right, and an 80% chance that they would get it wrong on the first question. On the second question, same deal, 20% right, 20% wrong. Third question, 20% and 80% that they would get it incorrect. In other words, they just guessed the answer. 5 choices, they just guessed the answer. We would work out very similar to our coin problem, except that the probability of a correct answer would be 0.2. Probability of incorrect answer would be 0.8. So as you added up all of these different possibilities, you can figure out the probability of getting 3 correct is going to be 0.2 times 0.2 times 0.2, so it's 0.08, a little less than 1%. Probability of getting all 3 incorrect is going to be a little bit more than 50%. You add up all the probabilities when you add up and then you go across and look at the results, and it'll add up to just like before. Okay, so one of the things that you might also do is what if the probability of getting questions right and wrong are different for each question? So the first question might be 0.2 and 0.8 for correct and incorrect. Maybe it's 50-50 on the second question. So you can build a probability tree where you can solve almost any kind of probability that you would have. So I won't worry about that too much right now. You might see a little something like this on the test. So it might be worth going back on the home, like exercising a little bit. But if you do see it on the test, it's going to be like fairly simple. Okay, so I'm going to move on from that. Okay, let's talk about this idea of conditional probability. Here's a chart. Okay, and again, keep in mind what we're looking at the number of possible outcomes that satisfy your criteria out of the number of samples that you took, coins you flipped, or questions you answered, and so on and so forth. On this particular table that you see behind me, I'm going to blow it up a little bit so you can see it better. Okay. Okay. If a person is randomly selected from this population, this is the U.S. population, maybe 1960 or something like that, 1970, 214 million people. These are millions of people. Okay, so we have 214 million people. We're just going to look at this 214 for our purposes. If one person is randomly selected from this population, from the United States population, what's the probability that that person is divorced? Well, let's see what we got here. How many people are divorced in the United States in this sample? 21%, 22% roughly. Out of 214 million, right? 21 million, 21 or 22 million, or 214. So what percentage of the population is that? It's 21.7 over 214, which is about 10%, right? Probably nowadays, probably nowadays, that percentage is much larger than it was in 1960, right? Everybody agree? Okay. Okay, what's the probability that a person in this population is male? Just give me the fraction. 100 and what? 104.9 over 214.2. Right? That's the number of males in the population over the total number of people in the population. That's the probability that you randomly select a male person. What's the probability that a person, they randomly select a person who's both a male and a widower? Okay, what is that? Is that union or intersection? That's it sounds like union, right? Because you put it's really intersection. It's both, right? Not if they were just males and they were a widower, they wouldn't be a union. So it's intersection. So intersection, probability of A intersection B, where A is a male and B is a widower. Okay, what's the probability of selecting a person as male and a widower? 2.7 million over 214.2 million. Anybody have an issue with that? Sound okay? Okay. Okay, now I want to hear from the peanut gallery. Anybody know what the peanut gallery is about? You don't know what it's from? Anybody at all? No. It goes back further. No one in this room. When I was a kid, one of the first TV shows that was on was Howdy Doody. And they used to have kids in the audience. And they usually refer to the kids in the audience as the peanut gallery. Okay, so ask your grandparents. I'm sure they were. So at any rate, I have to explain these things because as I get older and you people get younger, fewer references than I make sense to you guys. Okay, so I want to hear from the peanut gallery back there. Okay. What's the probability? Given that a person is male, what is the probability that he is married? Before you answer that, what kind of probability is that? Conditional probability. That's what we were talking about. Given that a person is male, in other words, first we determine that person is male. Now we're only looking at male. So what's the probability that he's also married, given that he's male? Okay, so what do we got here?
63.5.
Got 63.5 married males over the total number of males, 104.9. Perfect. You've done your first conditional probability correctly. That's what a conditional probability is all about. What if I had said, what's the probability of being widowed if you're a female? What would that be? 11.3 over 109. In other words, we're only looking now at the first condition to be satisfied is now to 109 million people, and added that 11.3 million of them are females. 11.3 over 109. Okay, is everybody comfortable with that? Okay, that's really what conditional probability is. conditional probability is that simple a concept. Yes.
Is it given who's, like, if you're widowed, how many people?
Sure. Given that you're widowed, what's the probability that you're a female? Given that you're widowed, how many people are widowed? 14 million. Out of those, given who are widowed, how many of them are female? 11.5. What's the conditional probability? Given that you're widowed, what's the probability that you're female? It's 11.3 over 14 million. Okay, so you can do it either way. Remember, we mentioned that. It's a different probability than saying the probability of being widowed, given that you're female. That was the point Levi was making before when he said the probability of A given B is different than the probability of B given A. Right? We just did that right now, didn't we? The probability of being widowed given you're female is not the same as the probability of being female given that you're widowed. Right? I think I got that right. I didn't mix them up. Okay. Trust me, it's hard for me to keep this stuff straight nowadays. So at any rate, so that's what we're looking at. Conditional probability is an important concept. And it's important in this idea of probability, in this idea of a diagnostic test. Let me see how guys are doing online. Okay, Alicia, sorry I didn't see that question, but yeah, I think you're right. 0.2 times 0.2 times 0.2. Okay, so I'm going to move on. You guys online can still see me and hear me, correct? Okay, good. All right, so now let's move on to diagnostic tests. Okay, and I'm going to make up a diagnostic test, and this is a document you have online. And this is kind of, we're going to step through this idea of a diagnostic test. Maybe even blow this up. I wish I could remember how to get rid of all these ribbons like that. Where do I do that? View, ribbon. Oh, there we go. That's better. Okay. Let's go to 300%. I went to, yeah, for the screen. How about now? Okay, good. I think you guys can see that going across. Except for me, I got this other window blocking it. Okay, so a company creates a diagnostic for nickel allergy, nickel sensitivity. Nickel sensitivity is increasing at a breakneck speed because people are getting, what do you call it? Piercings and so on and so forth. A lot of them have stainless steel, have nickel in the compounds, even some of the silver compounds have a little bit of nickel. Nickel happens to be an allergen for a lot of people. I know I can wear a watch because, I can't wear a watch. I was about to say I can't wear a watch because the stainless steel back gives me a rash. Stainless steel has nickel in it. This is an Apple Watch. It's the cheapest Apple Watch. What do they make the cheap Apple Watch? Aluminum. So I can't get away with wearing this. Right? So I have a new toy. I wasn't going to buy one until I saw that the really cheap one happened to be actually was teaching me it was aluminum. So far I haven't gotten a rash. We'll see. Testing that. So at any rate. Okay, so a lot of people get the rate of nickel allergies is increasing, which is becoming more of a concern. A lot of implants, may have chrome or nickel in them and so on and so forth. So there's some concern that there may be issues with nickel amalgam, implants and piercings and so on and so forth. Okay, so they produce this test, and they give it to, they take 100 subjects they know are sensitive to nickel, and they test them with this. They perform this diagnostic test. Very simple diagnostic test. Right? Diagnostic tests are always a problem because sometimes they're expensive, they're invasive. You're always looking for a really simple test to screen people for a disease, nickel allergy test type. They find that it correctly identifies 80% of the people that have a nickel allergy. In other words, out of that 100 test subjects, it got it right with 80% out of that. So what happened with the other 20? What did the test came out negative, right? So they got almost negative. those persons, those 100 people, they know have a nickel allergy. So when they only got 80 right, they know the test is only effective 80% of the time at identifying people that have a nickel allergy. Okay, that 80% is called the sensitivity. If you have 100 people have a nickel allergy, and the test, and you give them this test, 80% of the time it'll identify those people. It'll identify 80% of the people that's having a nickel allergy. If you had, let's say, I gave a screening for prostate cancer, right? And that might be a sensitivity of, say, 60%. Well, what does that mean? That means that 40% of the time it'll miss people that have prostate cancer. 60% of the time it'll correctly identify people that have it. So specificity, it refers to people that actually have the disease. How good is the test at identifying it? There's another term we use that you heard in the lecture called sensitive. The other term you heard is specificity. Specificity is how good it is at identifying people that don't have the disease. Okay, so now we take 100 people that we know are not sensitive to nickel, we give them the same test. 10 out of 90 times it says, oh, that person's sensitive to nickel. It's wrong 10 out of 90 times, right? The 90 times you got it right are true negatives. People that don't have the disease, and it was right, it identified them as negative. Okay? The 10% of the times that it got it wrong were false negatives. It says that they were they're right, false negatives. I got false. They are, let me think about this for a second. They're false positives. They don't have the disease. The test said that they did have the disease. So you're right, they're false positives. Okay, so I have a head cold, so it confuses me sometimes. That's as good as an excuse as any. Okay, so we're going to apply, we know now this test. They've demonstrated that this test has an 80% sensitivity and what did I say, 90% specificity. Okay, we're going to apply this test to a population. Okay, let's apply this. Okay, first of all, when we draw this table, our diagnostic table, our crosstabs, or contingency table, we always kind of set this up so that the test outcome is in the rows, and whether the person has the disease is in the column, right? So everybody in the top row tested positive. Every bottom row tested negative. Everybody in the first column is sensitive to nickel. Everybody in the second column is not sensitive to nickel. Okay, and then the totals, we can add up the totals of the various columns. Okay, so let's go ahead and actually work on this. Okay, so I'm going to make up a bogus population, randomly select a population, a sample in this population of 1,000 people. What did I say prevalence of nickel sensitivity was? Remember what I said there? I'll go back. I said that in this particular population, no, that was a sensitivity before. I said that the sensitivity in this particular population for nickel, the prevalence of nickel sensitivity is 20%. That means 20% of the people are sensitive to nickel in this population. So I randomly select 1,000 people. How many of those 1,000 people would I expect have a nickel sensitivity? 20% prevalence. How many would I expect? 200, right? 20% of the population I would expect to have a nickel sensitivity. And out of those 1,000, I would expect 800 would. So I already filled it in over here. Okay, how many sensitive to nickel? Remember, everybody in that first column are people that have disease, sensitivity to nickel. People in the second column don't have disease. So if we randomly sample 1,000 people, 200 are going to be sensitive to nickel, and the 800 are not going to be sensitive to nickel. Anybody remember what the sensitivity of this test was? 80%. So if 200 people are sensitive to nickel, and we get the test right 80% of the time for people that have the sensitivity, how many people out of those 200 are going to be positive? 160, 80% of those, right? How many are going to test negative? 40. Okay, what are those 40 called? False False, what is it? False negatives, exactly. They tested negatives and the false negatives. Okay, so now out of the 800 people that are not nickel sensitive, what did I say the specificity was? 90%. So it's going to get the test right 90% of the time. How many people is that out of 800? 720. Where does the 720 go? In the top or the bottom? Well, it goes in the bottom, right, because that's the right test. That's true negative. How many people are test positive in the population of 800 people that don't have it? That's going to be the remaining 80. Okay, so now let's fill in the last part of that list that we had. How many people have tested positive altogether? 240. How many people have tested negative altogether? 760. Everybody agree so far? Okay, you guys agree on that are online, right? Everybody comfortable with this so far that are online? Okay, great. So now I'm going to ask you the next question. I'm going to scroll up here, and hopefully I didn't fill in too much of this. Yeah, okay. So the next question is going to be, what's the positive predictive value of this test? What is positive predictive value? Positive predictive value is if you get a positive test, what's the probability that you really have the disease, right? How many people got a positive test in this population? 240. Out of those 240, how many of them actually have the disease? 160. So what's the probability you have the disease if you tested positive? 160 over 240. That's, and what is that? That's 0.67, right? 0.666, whatever. That's the positive predictive value, right? So in this particular test, with this particular sensitivity in this particular population, the positive predictive value of this test is 66%. That means there's a 33% chance if you test positive, you don't have it, right? Okay, what's the negative predictive value? Let's think about this. The positive predictive value was how likely it is you have the disease if you test positive. Negative predictive value is how likely it is you don't have the disease given you tested negative. How many people tested negative? And how many people were actually negative in that population? 720. So 720 over 660 is your predictive value. Okay. If you look at that in terms of like, it's a lot more intuitive, listening to it that way, than looking at the formula. Positive predictive value is the number of true positives over the true positives and false plus false positives. In other words, the total number of positives. Yes.
Are the true positives determined by like people that have like a gold standard test and something like
Yeah.
that?
Well, that's how they did the original study to figure out the sensitivity. You would use the gold standard. So what would happen now is that if there was an invasive test for nickel, like for instance a challenge test, you guys know what challenge tests are, right? Like in other words, if you have something you think is asthmatic or something like that, you spray something with a dust that produces asthma or something like that, you'd be challenging them. And you don't want to do that because they could die, right? Matter of fact, I think there was a study it might have been in your ethics course where was there a study like that you guys saw? Yeah, there was a study where a student that was volunteering or to make an extra few bucks or something like that in an asthma test was challenged to the state and sprayed them with some allergen or something like that, or to use some sort of drug on them or something, and then tested them out that way, and they died. They literally died. So that happened, and they didn't really, inform her of the dangers, hazards, or anything. It was a real mess. That's why they have. And when you read through all these things, this mess, and you would think that like that doesn't happen anymore. Trust me, this kind of stuff still happens. There's a study that's probably there about the early and testing of trying to insert genes using viruses that involved someone had some sort of immunosuppression or something like that. Also was a disaster. But at any rate, another way of saying negative predictive value is the the true positives over the total number of positives, which are true positives plus false positives. Negative predictive value, another way of saying that is true negatives over the total number of negatives. True negatives plus false negatives. Yes.
Isn't it just like, could we say it as a conditional probability? Like,
Ah,
The probability that you're not going
say that again. Say louder.
what, can you say it as a conditional
It's
probability?
exactly a conditional probability. The probability of the positive predictive value is the probability that you have the disease given that you tested positive predictive value. Negative predictive value is the probability that you don't have the disease given that you tested negative. Now, see where this all ties in together now. Positive predictive value, negative, they're conditional probability. Now we're really going to clear the mess down by looking at Bayes' rule in a second. But before we do that, we got to take a look at another important function here. I hope you guys got that online also, that this idea of positive predictive value being a conditional probability. We'll dive into that a bit more. The next thing I want to do is I'm going to take the same test exactly the same. 80% sensitivity, 90% specificity. I'm going to apply it to a new population. The prevalence of nickel sensitivity in this population is only 1%, right? So I'm going to randomly sample 1,000 people in this population. How many people are going to be sensitive to nickel in this population? 1% out of that 1,000. How many is that? Somebody take a wild guess. 10, right? 10 people. Okay. All right, good. Okay. So, you guys online, if you answer first, you get like extra consideration. So 10 people are going to be nickel sensitive in this population out of 1,000 people. If we apply this test to those 10 people, how many of them are going to test positive? 8 people, right? 80% or 8 people. How many people are going to test negative? In other words, how many false negatives we have? 2. Okay, now, what does that leave? That leaves 990 people that don't have a nickel sensitivity. Okay, the specificity is 90%, still the same test. So how many people out of 990 would test negative? It's easier to figure out what percentage are going to test positive, because that's going to be 10%, right? 90% going to test negative, 10% going to test positive. So that's going to be 90, right, up there. And what's that going to leave down here? 99. I'm sorry, 99. And what's that going to leave down here? It's going to be 800 and, am I right? 891. Okay, that adds up to 800, 990. Okay, so how many people in this population with 1% prevalence, same test exactly, only difference is the prevalence of the disease, the sensitivity to nickel. So how many people in this population tested positive? 8 plus 107, right? How many people tested negative? 893. Good. Okay, so now let's figure out our positive predictive value. How many people tested positive? 107. Out of those, how many of them actually have the disease? 8. So what's the positive predictive value now? 8 over 107, which is roughly, what is that, about 8%, I guess, right? Close enough, about 7%. What happened? In other words, if you take this test and you test positive in this population, right? It's only 7% chance you actually have the disease. So you're going to send somebody on for more invasive testing based on this result. What happened? What was the only difference between this population and the other population? The prevalence. The prevalence. So what does this mean? This means that even when you have a pretty good test, 80% sensitivity, 90% specificity, even when you have a good test, if you have a disease with a very low prevalence, you're going to have relatively low positive predictive value. Give me a couple of examples in real life of tests that they use frickin' everywhere, and you know a dozen people that have gone freaking nuts because their doctor said, oh, you tested positive now, you got to go and you got to sweat out this more elaborate test, the more invasive investigation and so on and so forth. For men, a prostate, exactly, PSA. and relatively relatively low incidence of actual prostate in within say certain age ranges, 40 or 50 or something like that. But PSA, like you wind up testing a very large population. They start at 40 or 50 or something like that. Very large population with a low prevalence. When you get up to 70 and 80, prevalence much higher. Well, when you get to that younger group, prevalence is pretty low. How about with women? What's that? Mammograms? Yeah, mammograms. What else? Pap smears, right? Right, they're almost universal, right? Very low prevalence rate in women within most age ranges. Right? So what happens? Get a lot of positive pap smears. Then what happens? You have to go up, you got to go through follow-up testing and so on and so forth. So I'm sure you guys have had experience with, if not yourself personally, with people you know that have had, biopsies and other tests and so on and so forth, found out that that screening test that they took was inaccurate, wasn't correct. I don't know what this is, so I'll make it go away. Okay, so that's our positive. What's our negative predictive value while we're at it? I can't hear that. It's too low back there. Forget it. Too many rock concerts, and you got to talk louder than that if you want me to hear that.
891 over
891 out of 893. In other words, the number of correct tests, correctly identified people, over the total number of people that tested negative. Again, how does that relate to a conditional probability? For the positive predictive value, it's the number of people that actually have the disease, which was 8, given the number of people that tested positive, which was 107. And for the negative predictive value, it's the number of people that don't have the disease over the number of people that tested negative, given that they tested negative, which was 893. Okay, good. So we got a very interesting look at this whole thing. There's also a couple of links to articles on diagnostic tests on diseases with low prevalence in the population. Okay, and next time you go for a test, I challenge you. The next time you go for a test, when you get the test, whatever it happens to be, I have to go to teach a course at Rutgers. Not a course. It's like 2 days. I have to teach 2 days worth of. They make me go through a background test, a physical. I have to go next week for a patch test. I don't know if they call it. They still call it a patch test, TB test, skin test. Like they challenge you on, they scratch you or something like that. They challenge you to go back 2 days and see if you have a reaction or something like that. They used to call it in the old days a patch test, right? I have to go for one of those because I teach 2 days down there. They want to make sure I don't have TB. At any rate, what was I? How did I get off on this? Next time, you don't have to go for that test. The next time, when I go down there for that test, I'm going to challenge them. I'm going to ask them, hey, what's the positive predictive value? What's the negative predictive value? Let's see if they actually know. And my guess is they're going to know. They won't want to tell you, but they're going to know. Yes. Yes. Yeah, I think you're right. Yes, it probably will be, won't it? Because think about it. The lower the prevalence is, the more of a chance of getting wrong on the positive predictive value. You have more people that don't have the disease that you're giving the test. So that's kind of why this happens. Right, exactly. Exactly right. So that's kind of like the way you're getting a good idea of how this whole thing's working. Okay, so now let's look at Bayes' theorem with that really nasty formula that we saw before. And maybe we can apply this test to it. Okay, now here's Bayes' theorem. In fact, let's try and apply one of these. See if we get the same answer. We got another version of this. Okay, here's Bayes' theorem. Here it is in two different ways, which are absolutely equivalent. Let me get this out of the way. Bless you. I want to do that in the worst way myself. Let me tell you. You probably tell I'm trying to get an overhead cold. So, at any rate, Bayes' theorem. Probability of B given A has occurred is equal to the probability of A given that B has occurred times probability of B over the probability of A. That like really goes nowhere. That goes over like a lead balloon. Right? I mean, you say that and it's like meaningless, right? It's the same thing as saying the probability of A given B is equal to probability of B given A and probability of A over the probability of B. All we've done is reverse the A to the B step. Right? So you can work it both ways. Remember we just talked about, well, what about if it's given that they're widowers and what's the probability they're females versus given that they're females versus the probability that they're widowers. Right? That would be both both situations. Probability of A given B and probability of B given A. Right? We actually looked at that in real life. Okay, but so it doesn't really matter which you could actually just instead of using these two different formulas, you could just use one version of it and just switch around which one is A and which one is B and actually work it out. So we're going to actually work it out. Okay, so the formula starts out this way. Okay, let me make this bigger if I can. Let me see it. Okay, and I'm going to make this one bigger if I can. Okay, and I'm going to try and explain what the difference here without making you guys crazy or like giving myself a headache. Okay, probability of A given B given that A has occurred is equal to probability of A given that B has occurred times the probability of B over the probability of A. Let's apply this to a diagnostic test. If I apply this to a diagnostic test, okay, and there's the diagnostic test right below it. Probability of you have the disease given that you tested positive, a positive test. Okay, well that's my positive predictive value, right? Isn't it like right here where I'm looking right here? Isn't that my positive predictive value? You see that arrow circling? Yes. I want sometimes I don't know what's going on behind me there or online. Okay, that is the probability that you have the disease given that you tested positive. Positive predictive value, right? It's another way of positive predictive value. So so if I look at it from the perspective of this formula up here, okay, what is B? B is disease, right? Disease plus, you have the disease. A is the test, positive test, test plus, right? That's what those two are. Make sense? Okay. So let's see what we got up here. We got the probability of A given B has occurred. In other words, the probability that you test positive, probability that you test positive times the probability you have the disease, right? That's the opposite of these two. See, it's the E given T, probability of disease given that you test positive is equal to, this is B given A and this is A given B. So this is T given D. Probability you test positive given you have the disease times the probability of B. What's B? Probability that you test positive, right? Excuse me, probability that you have the disease. Remember, it's B given A. Probability you have the disease is this. This is the probability of B up here. So this checks out, right? When we compare it to this checks out. We don't have D prime yet. We're about to get there. I'm just looking at the top, the numerator. Right? Everybody comfortable with the numerator? Yes. The probability you have the disease if you test positive, given you've tested positive, positive predictive value. And what is that equal to? If we put it into Bayes' theorem's formula, we see that it's the opposite. A given B, probably having the disease given that you tested positive. B given A, okay, is equal to the probability of A given B, or in other words, probability you test positive given you have the disease, times the probability of the first one, which is disease, probably you have the disease. Okay, so the top part of this we're comfortable with. But what is the top part of this? Well, now I'm going to open this thing up down here, and we're going to see something really interesting. If I can get this to work. Let me blow this up. So it goes up the whole page. Come on. Oh, you know what it is? I'm holding this thing, I think. Oh, no, that's what it is. I'm going to turn that off. Let me expand this a little. Come on, give me a break. There we go. Now this is going to get really interesting now. Okay, so what do we have? I'm sorry it's so low on the screen here. Hopefully, when you get a chance to go home, you see it. So what's on the top here? What is the probability? Now we got to change this back again. There we go. Okay, what is the probability of testing positive if you have the disease? That's the sensitivity, isn't it? So this is the sensitivity, right? Times the probability you have the disease. What's the probability you have the disease? It's the prevalence. So we actually know that from this population. I'm going to take the first version of it that we did with the 20% prevalence, okay? The sensitivity of the test is 0.8. The prevalence is 0.2, right? 20% prevalence in that population. Now, what about the bottom of this formula? How the hell do we get from probability of A, which that you test positive, down to this mess on the bottom, right? Well, let's see how we got there. How did you test? Who tested positive here? Well, the people who tested positive are people who had the disease. So if I look at this first test here, right? This is the probability that you have the disease, right? That's in this case, it's 20% of the people, right? Well, this is the probability that you test positive given you have the disease. That's the sensitivity. So we're multiplying the sensitivity times the prevalence, which gives us the percentage of people that would have that if they have the disease would test positive. 20% of people have the disease, and we get it right 80% of the time. So this is basically the sensitivity times the prevalence. Yeah, isn't it? It is, right? It is exactly the same. Sensitivity times prevalence. So this is the percentage of people that tested positive given that they actually have the disease. Who else tested positive? People that don't have the disease also tested positive. They're part of that probability of testing positive, that A, that positive test. Well, how do we determine which people don't have the disease? Well, let's see. First of all, it's going to be the probability of not having the disease. Well, that's 1 minus the prevalence. So this is going to be 0.8 times 0.2. Right? So 1 minus the prevalence. What was the prevalence? The prevalence was 80%. 1 minus the prevalence is 0.2. Times, well, who tested out of that group that didn't have the disease, what percentage of them tested positive? Well, if we wanted to know what percentage of them tested negative, we'd use the specificity. But we want what percentage of them tested positive, so it's 1 minus the specificity, which is, instead of being 0.9, which is the specificity, 1 minus is going to be 0.1. Right? Okay? I know this can be a little confusing. So what does this all boil down to? It boils down to 0.8 times 0.2 is 0.16 over, and these are the two groups that tested positive down here, but where we got our positive, the probability of testing positive came from. Among the people that had the disease, it's 0.8 times 0.2, which is 1.6. Excuse me, I'm sorry, 0.16. Don't let me get away with stuff like that. We'll never get out of here. Trust me, I know from previous semesters. Times the probability of not having the disease and testing positive, which is 1 minus specificity times 1 minus prevalence, 0.1 times 0.2 is going to be 0.02. Am I right there? 0.02. Everybody agree with that? 0.02. I'm sorry. Did I make a mistake there somewhere? Because I'm sorry, that should be 0.8. Yeah, that should be 0.8. 1 minus the prevalence should be 0.8. So that should be 0.08. So what does that come out to be? It comes out to be 0.16 divided by 0.24, which is how much? 0.67, right? right? And that's the prevalence. Isn't that what we got for positive predictive value the first time we did it with a 20% population? We got the same answer. It was tortured this way, but we got the same answer, right? A little bit torturous, right? But we actually here applied Bayes' theorem to a conditional probability that involved a diagnostic test by not knowing the real actual numbers of people that were involved, but by applying what we knew about the sensitivity, prevalence, and the specificity. That's all we knew. If we knew the sensitivity, prevalence, and the specificity, we could then predict the positive predictive value without actually knowing the number of people in that population. And what might change this? Well, if the prevalence is different, it's going to. If we did this again, we put and we use the prevalence of point of 0.01, we get the answer for the other population that we tried. What else might change it? Well, if the specificity were different, it would change it. If the sensitivity were different, it would change it. But in any case, we actually applied this. If we're really good in life, we'll never have to do this again. Okay, so I think on the test you might get if you see this on the test, it might be a little sugar coated. I might actually give you the version of it that shows the sensitivity and the prevalence and stuff like that, rather than to make you go, back to scratch on it. Okay, so I think we're up to about 8 o'clock, and I'm going to start. I want to start to answer some questions, maybe go over a little of the homework. So for starters, on this material right here, questions. Got to be some questions, right? I can't be that good at this. Sure. How about you guys online? Why 1 minus the prevalence? There's a good question. It was 1 minus the prevalence because that second part after that plus, see the two parts of that plus down there in the denominator. This part, this is really basically what is this? This is the number of people that tested positive, right? Over the number of people that tested positive that had the disease, and plus the number of people that tested positive that didn't have the disease, that were really negative. So this is the number of people that tested positive that have the disease, and that's the prevalence times the sensitivity. 20% of the people have the disease, and you're right, 80%, 0.8, or 80% of the time you're correct at getting a positive test. So the number of positive tests you get based on that, the percentage of positive tests is 0.8 times 0.2. This is people that don't have the disease. How many of those people are going to test positive? Well, for starters, the prevalence was 20%, right? But we're interested in the people that don't have the disease. That's 80% of the people. That's why we took 1 minus the prevalence. We're interested in those 80%. Well, the specificity is the probability that those 80%, in other words, the specificity, which is 90%, probability that they would test negative. But we're not interested in probability that those 80% that don't have the disease would test negative. We're interested in probability that they would test positive. So 90% they test negative, 10% of the time, or 1 minus the specificity, they would test positive. So 80% of the people would test positive 10% of the time for an overall percentage of 0.1 times 0.8, which is 0.08. So we got 0.16 from here, got 0.08 from here. So the bottom became 0.24, and the top, of course, was 0.16. So out of every 1,000 people, 160 people tested positive that actually had the disease out of 240 people that actually tested positive. If you go back there, you'll actually see that in the chart. That's why I use a nice round number like 1,000 when I did that.